So so I will be speaking about rationality for W-algebras. Let's see. Okay. So these are W-algebras are examples of vertex operator algebras. So probably these objects are not familiar to everyone here. So I should start by saying a little bit about what a vertex operator algebra is. So first of all, it's a graded vector space. Usually we like it to be Z-graded, though sometimes we like it to be half Z-graded. There are different options here. And then there's this vertex operator map, also called state field correspondence. So the vectors in V are called states, and then this this vertex operator is called a field. So to any pair of vectors in V, we associate a formal series, a formal Laurent series whose coefficients are vectors in V. There's a vacuum vector, which is in the degree 0 component, and the vertex operator associated to the vacuum is the identity operator. We also have a conformal vector living in degree 2, and the coefficients of powers of x in the vertex operator for omega span a representation, span the Virasoro Lie algebra. The commutators of these operators satisfy the Virasoro Lie algebra relations with some central charge scalar C. And then since I mentioned the grading up here, I should say that the degree n space in V is the eigenspace of the L0 operator with eigenvalue n. And there are a number of further axioms and relations that we want this data to satisfy, in particular for the vertex operator. Maybe what I will highlight here is this complex analytic commutativity and associativity relation. The commutativity relation is also called locality, where if you compose vertex operators in different ways, and you interpret the formal variable as complex numbers living in non-zero complex numbers living in certain domains, then you get certain series in powers of Z1 and Z2, which converge in certain regions to the same function. That's the meaning of the tilde, is that they converge to analytic continuations of each other. So this is roughly what a vertex operator algebra is, and some motivation for these kinds of structures. I guess maybe the main motivation these days is that vertex operator algebras are an algebraic approach to studying two-dimensional conformal quantum field theories. So the so-called chiral algebra of a 2D CFT is a vertex operator algebra, essentially. And another motivation is this theorem by Huang, which states that the category of representations or modules of a sufficiently nice vertex operator algebra, sufficiently nice is this strongly rational here, it is a modular tensor category. So what goes into a modular tensor category? Well, it's a semisimple category, so every object is a direct sum of simple objects. There are finitely many distinct simple modules. And then there is this tensor product operation. There's some way of taking a tensor product of two modules in your category. And this tensor product operation has a unit. it has a tensor unit, which is the VOA itself, is associative in a naturally associative. It's rigid, which means that every module has a dual in some suitable, strong sense. And there's a non-degenerate braiding. Braiding means that the tensor product operation is commutative. And I will say a little bit more about what non-degenerate means later. So Huang's theorem says that VOAs give you modular tensor categories, and modular tensor categories are interesting because there are many applications in low dimensional topology, such as knot invariance, three-manifold invariance, topological quantum field theories, and so on. So, in that sense, VOA should be interesting as giving you examples of modular tensor categories. And in fact, there's kind of a conjecture, which is a kind of converse to this, which is that every modular tensor category is equivalent to the module category of a strongly rational vertex operator algebra. If you want, you can add extra structure such as a unitarity. You might also ask whether every unitary modular category is the module category of a unitary VOA. And if you want to consider unitary categories, there's also this other approach to CFT using von Neumann algebras and these so-called conformal nets, which I will just briefly mention here. But anyway, this conjecture is certainly wide open, and I won't really say anything much more about it, except just to say that certainly if one wants to see whether this conjecture has any hope of being true, then it would be good to have a large supply of rational VOAs so that, if you come up with a new modular tensor category, you have some chance of, finding some VOA that gives rise to it. But I guess the problem with this is that it's much easier to construct VOAs than it is to show that they are rational. So the question is whether there's some checkable criteria for showing that a vertex operator algebra is rational. So yeah, so far I haven't really given the definition of rational VOA. Before I do that, I should say something about modules for vertex operator algebra. So a module for a VOA is some graded vector space, again, graded on which the VOA acts naturally in some sense, which means that we also have this module vertex operator for any vector in V and any vector in W. We have this, again, a formal Laurent series where the coefficients are vectors in W. So V is acting on W in this way. And the axioms of a module are similar to the axioms of VOA. You have the vacuum. If you put the vacuum into the module vertex operator, you get the identity. There are similar commutativity, associativity, and Virasoro properties. And I would like to mention in particular that the degree H subspace of a module is, again, an L0, but it's in general, we allow it to be a generalized L0 eigenspace. L0 may not act semi-simply on a V module, not necessarily. And this seems to be a good point to mention contragradient modules. If you have a module W, then you can take the graded dual vector space, and then that has a natural structure of a V module. So now I can say what is a strongly rational vertex operator algebra. I guess the name comes more or less from the fact that these are the VOAs that show up in rational conformal field theory. So the properties, there are some, first of all, there are a few minor properties. One is this positive energy or CFT type condition, where we want to say that it's non-negatively graded, and the degree 0 space is just the span of the vacuum vector. So if you think of L0 as measuring the energy of a state in the VOA, then this kind of VOA has positive energy. It should be self-contragradient, it's isomorphic to its contragradient as a module for itself. It should be a simple vertex operator algebra, no non-trivial ideals. This follows from the first two conditions, actually, so it's automatic. And then there's this important but technical C2 cofiniteness condition, which is that the dimension of a certain quotient vector space should be finite, and the subspace we are quotienting out is spanned by these -2 indexed operators acting on vectors in V. So this is some technical condition, but essentially gives some finiteness conditions on the VOA and its category of modules. And then finally, this condition of rationality, which is just that the category of V modules is semisimple. And I will note here that this last condition of rationality is really the only one that is not intrinsic to V. So it's natural to ask whether this condition could be replaced with something that's more intrinsic. That's one of the problems with proving rationality, is that you may not be able to prove that a VOA is rational until you understand enough about its representation category. But if you can replace this with an intrinsic condition, then you just have to understand V itself well enough. So we can remove this rationality condition from the definition of a strongly rational VOA. So keep all the first four properties, but we remove the rationality condition. So it's convenient to call such a VOA strongly finite if it has these C2 cofiniteness conditions and the other three minor conditions. So here is a list of some of the important properties of strongly finite VOAs. So the first of them has to do with, so the Zhu algebra of a VOA, which is introduced by Zhu, is a associative algebra structure on some quotient of the VOA, which I won't go into detail about the definition, but essentially the Zhu algebra describes the way a vertex operator algebra acts on the lowest degree space of a V module. So it turns out that simple modules of A of V, the Zhu algebra, are in one-to-one correspondence with simple modules of V itself. In the case of a strongly finite VOA, this associative algebra is finite dimensional, so the category of modules for a strongly finite VOA has there's finitely many simple modules. In fact, we can say more. Huang proved that the category of modules is a finite abelian category. So not only are there finitely many simple modules, but every not necessarily simple module has finite length. Every simple module has a projective cover, and so on. And also, this category has a structure of a braided tensor category. So the conjecture that's been made by a number of people is that the module category of a strongly finite VOA should not just be a braided tensor category, but it should also be rigid. And the braiding should be non-degenerate. So sometimes categories like this are called non-semisimple modular categories. I guess it really should be not necessarily semisimple modular tensor categories. So maybe to avoid that confusion, I'll refer to them as factorizable finite ribbon categories. So it's another term in the literature for this kind of tensor category. So the question is, we have removed this semi-simplicity condition. So the question is, how can we tell when this semi-simplicity condition actually does hold, and thus we get a semisimple modular category and a rational VOA. So let me say a little bit more about how we actually get tensor categories from vertex operator algebras. The first thing to say is that tensor products of modules for VOA don't come from the vector space tensor product, which does not have a natural V module structure. But instead, it's based on intertwining operators, which are essentially a VOA version of the notion of bilinear map between vector spaces. So it's some kind of map, some kind of bilinear map, which takes vectors in one module, vectors in another module, and gives out a formal series with coefficients coming from a third module. And we allow the series to be much more general than just a formal Laurent series. We allow complex powers of formal variable and also finitely many positive integer powers of the logarithm of formal variable. So these intertwining operators satisfy properties similar to the vertex operators for VOA and its modules. There's some, again, some kind of complex analytic commutativity and associativity property. So once we have this notion of intertwining operator, we can define what a tensor product module is. It should be some pair of a module and an intertwining operator going into that module, which satisfies some universal property like this. For any intertwining operator going into a third module, W3, it should factor through this tensor product module. There should be a unique V module homomorphism coming from the tensor product going into the third module. So this would be similar to the definition of tensor product of vector spaces using bilinear maps. So here we use intertwining operators and a universal property. So if we have a tensor product, if we have this tensor product operation on a category of modules for VOA, and it's not necessarily easy to show that a category would be closed under tensor products because defining some object by a universal property doesn't imply that the object actually exists. But if you can show that the tensor product objects do exist, then it's easy to construct tensor products of homomorphisms. It's easy to show that the VOA itself is a unit with respect to this tensor product, and that this tensor product is commutative. There's this ribbon twist that you get by exponentiating L0. The associativity of this tensor product is much more difficult to prove. Basically some complex, it has to do with complex analytic properties of intertwining operators and is related to general operator product expansions in CFT. So if we assume that a category of modules for VOA has the structure of a braided tensor category, well, maybe we would like it to be a modular tensor category so we can get things like 3-manifold invariance and TQFTs and so on. Well, we need further properties, in particular this rigidity and non-degeneracy for the braiding. So let me first say what rigidity means in a little more detail. Rigidity means that you have to have a dual for every module in your category. And natural candidate, of course, would be this contragradient module, which is constructed on the graded dual vector space. But you need more than just a candidate module. You need an evaluation homomorphism, which is a map from tensor product of the dual and the module into the unit object V. This is easy in many cases because to get a map like this, you just need to construct some intertwining operator that involves these modules. Based on the universal property, you then get a map. You also need a co-evaluation map going the other way from V to the tensor product of W and its dual. The existence of a map like this is not so obvious when the category is not semisimple. And then finally, there's this composition that you get when you this composition, which turns out to be an endomorphism of W, should be the identity on W. So this is rigidity. This rigidity property is not obvious because the associativity is involved in this composition somehow. And associativity isomorphisms are not trivial in this kind of tensor category. So that's what you need to prove to show rigidity. And then non-degeneracy of the braiding. So in a braided tensor category, you have some braiding isomorphism, which I call R, which takes W tensor X to X tensor W. Then you can do the braiding again, the double braiding, do the braiding again to get back to W tensor X. So in a so-called symmetric tensor category, this double braiding is just the identity on W tensor X. But the braiding is non-degenerate if this category is as far as possible from being symmetric. So that means this double braiding should very rarely be the identity. So if you can find some object W such that this double braiding is always the identity, the only way for that to happen is for W to be maybe some finite direct sum of copies of V. V is the unit object in this tensor category, so the double braidings involving the unit object always have to be the identity. But that's this is non-degeneracy means this is as far as possible from being symmetric. Okay, so now I will say what. So now the general theorems about strongly finite VOAs that I proved last year. First, if we assume that V is a strongly finite VOA and that this dual algebra A of V is a semisimple algebra, then in fact, we can show that this tensor category of V modules is actually rigid, and the braiding is non-degenerate. So this category is a factorizable finite ribbon category, or in other words, a not necessarily semisimple modular tensor category. So the proof uses many of the same elements of Huang's proof of modularity in the rational case, the case that V is strongly rational. In particular, I won't go into the details really, but the main tool is the genus 1 correlation functions in the conformal field theory that's associated to V. So these are Q traces or traces of vertex operators acting on V modules. And maybe I should just remind you that the conjecture is that one shouldn't need the assumption that the dual algebra is semisimple to get this result. The conjecture is that if V is strongly finite, then this category is a factorizable ribbon category. But unfortunately, some technical difficulties prevent us from proving this general conjecture so far. So then the second theorem is, under the same hypotheses that V is strongly finite and the dual algebra is semisimple, actually we can say more than rigidity and non-degeneracy of the braiding, actually the category is semisimple. So V is strongly rational, and its module category is a semi-simple modular tensor category. But yeah, I've split this into two theorems because the proofs are essentially quite different. For the second theorem, it's more just some fairly abstract algebraic argument. You can use a semi-simplicity of A of V to rule out non-trivial self-extensions of V modules. And then the key thing, though, is that we need the factorizability. We need the rigidity and non-degeneracy from this preceding theorem, because it's known that projective covers of simple modules in factorizable finite ribbon categories have some nice structure. And those properties allow us to rule out other non-trivial extensions appearing in this category. So we get semi-simplicity. So the main application of these general theorems so far is to the affine W-algebras that I mentioned in the title. So let me say a little bit about what these are. So these also showed up in Thomas's talk from last night, or I guess it was last morning for those of you who are in person. So the W-algebras are constructed from the data of a simple Lie algebra G, a complex number called the level, and then a nilpotent element in the Lie algebra. And the construction of the W-algebra is based on this quantum Drinfeld-Sokolov reduction, which is due to Fagan and Frenkel, and then to Katsurowan Wakimoto in the fullest generality. So you start with a VOA that's associated to the affine Lie algebra of G at level K. And you construct this new VOA, which is the W-algebra. And the W-algebra is defined as a homology of a certain complex. The complex you get by tensoring this affine VOA with some sort of free field superalgebra, and the differential in this complex is the coefficient of some vertex operator for a certain vector in this complex that depends on F. And then the zeroth homology of this complex is a VOA called the W-algebra, and then you can take its unique simple quotient to get the simple W-algebra associated to G and F at level K. So some examples, some of the basic examples of these, if you take the trivial nilpotent element 0, then this W-algebra is always just the original VOA that was associated to the affine Lie algebra. If you take G equals SL2 and you take the non-zero nilpotent element, which is the root vector, then what you get is a Virasoro vertex operator algebra. And then if you take SL3, there are two possibilities for non-zero nilpotent elements. One of them is the principal nilpotent element, which is a sum of two simple root vectors. And there you get the Zamolodchikov W3 algebra. And then you get these Brashkovsky-Polyakov algebras if you take the F to be just a single root vector of SL3. So all of these simple examples have been known in the physics literature for quite a while. So then to get rational W-algebras, it's helpful to take the level to be an admissible rational number. So these admissible levels are rational numbers which are greater than the dual Coxeter number of the Lie algebra. And And so the conjecture, which was originally formulated by Wakimoto and then generalized by Arakawa, is that this simple W algebra is strongly rational if K is an admissible level and F is in a certain nilpotent orbit of G, this nilpotent orbit depending only on the denominator of K, of the level K. And in fact, many cases of this conjecture have been proved over the last few years. Most importantly, Arakawa proved that this is true when this orbit happens to be the principal nilpotent orbit. And actually, OQ is always the principal nilpotent orbit for all but finitely many Qs for any given G. But there are many cases where where Q is small, where OQ is not the principal nilpotent orbit. So these cases of K and F and G giving these W algebras have been called exceptional when F is in the nilpotent orbit associated to K. And so what we can prove using the general theorems I stated before is that actually this full conjecture is true, that all of these exceptional W algebras are strongly rational. So a lot of it is just a matter of combining some theorems that have already been in the literature together with my recent general results. So by the theorems I presented before, it's enough to show that a simple W algebra is strongly finite and that it has a semisimple or dual algebra. C2 cofiniteness was proved by Arakawa a while ago, a few years ago, and then quite recently Arakawa and Van Eckeren proved the semisimplicity of the dual algebra. It's also not too difficult to show that these exceptional W algebras are self-contragredient, at least when you use the most natural conformal vector to define the contragredient module structure. But there is actually a problem where you have to do something additional, and that is that many of the nilpotent elements that show up in many of these nilpotent orbits OQ are these so-called odd nilpotent orbits. And in these cases, actually, the W algebra is not actually a Z-graded VOA in this case. It's actually half Z-graded or half N-graded. So it's not a positive energy VOA in the usual sense. And this does cause some issues, but fortunately it's not a serious issue. You can actually show that this is still a strongly rational VOA if you can find a new conformal vector such that the W algebra is N-graded. It's a little bit tricky to work with this because when you find the new conformal vector, the W algebra, the contragredient module structure depends on the conformal vector, so it might not be self-contragredient anymore. Sometimes you have to work with the old conformal vector if you want the VOA to be self-contragredient. Sometimes you need to work with the new one to get an N grading, but anyway, it works, and I found that all the nilpotent elements F, which arise as OQ for some Q, do actually, we can actually find such new conformal vectors. So that proves this theorem. So in summary, we do actually get a huge family of modular tensor categories from W algebras. Again, many of them were already known from the principal nilpotent element case, but many of these are also new. I guess the next question is, what can we say about these categories? And one thing to note is that they're not usually unitary modular tensor categories. So if you're interested in unitary ones, you may have to look pretty hard to find new ones in this family. Another thing we can say about the structure is that there is some relation between the W-algebra module category and this Kajan-Lustig category, which is the category of modules for the simple VOA associated to the affine Lie algebra of G at level K. So you can generalize quantum Drinfeld-Sokolov reduction to apply to modules, and it takes modules for the affine VOA to modules for the W-algebra. And so this Kajan-Lustig category for the affine VOA is known to be a semisimple braided tensor category. Conjecturally, it's always a fusion category, which means it's finite and semisimple and rigid. It's not always a modular tensor category, although sometimes it is. So we conjecture that it's conjectured that this category is always rigid, and this is actually known when G is simply laced, and as well as in some other cases. We also expect this quantum Drinfeld-Sokolov reduction functor to be a tensor functor, and in some cases this is known to be true. So that means that this category of modules for the W-algebra should contain a subcategory, which is basically this affine Lie algebra tensor category. And one thing to note is that the level K, since it's not an integer, this Kajan-Lustig category is not one of the ones that Kajan-Lustig studied originally in their original work. This is not one of the WZW model unitary modular tensor categories. But still, it's a nice braided tensor category, and we expect it to be equivalent to the category of modules for a quantum group at a root of unity, as is the case when K is an integer. So these are some of the properties that you would expect these W-algebra categories to have. And maybe to illustrate this is the case of SL2. These properties are all very well known for SL2. So the admissible levels look like -2 plus P over Q, where P is at least 2. And if Q also is at least 2, then the OQ orbit is the non-zero one. So you get Virasoro VOAs. The rational W-algebra is a rational Virasoro VOA at these CPQ central charges. And it's certainly known that this is unitary only when the difference between P and Q is 1. And then we have these Drinfeld-Sokolov reduction functors. Actually, we have 2 of them because CPQ equals CQP. This is the most basic case of Fagan-Frenkel duality. So we have actually this Virasoro category contains two affine SL2 subcategories. One for P over Q level and one for Q over P. And these subcategories together generate as a tensor category, they generate the entire Virasoro category. So you expect to see some of these similar properties in more general W-algebras. And then also you can consider the denominator 1. In that case, the level is actually an integer, and the rational W-algebra in that case is the rational VOA of SL2 at level P minus 2. And in this case, we get the usual WZW model modular tensor category for this for SL2 at this level, which is unitary. So maybe I'll finish with a few open questions. So if you're interested in unitary modular tensor categories, certainly an interesting question is when these new modular tensor categories from W-algebras are unitary. Usually they won't be, but probably in some cases they are, and it'll be interesting to see if they're any interesting examples. Another question is whether is when these new categories are actually not really new, but are maybe equivalent to previously known examples. So sometimes you do get coincidences where maybe some new W-algebra modular tensor category is equivalent to maybe one coming from a Virasoro algebra, for example. We can also go beyond admissible levels. There are actually some examples of W-algebras at non-admissible rational number levels that are strongly rational. And there are a number of other a number of others that some are known and others are conjectured. And yeah, so finally, most of this talk has been about rational VOAs, which have semi-simple representation theory. But if you want to go beyond semi-simplicity, then you can ask whether you can get interesting non-semi-simple tensor categories from non-rational W-algebras. And there, the answer is also yes, at least in some cases. For example, for the Virasoro algebra, you can look at the CP1 central charges. And it turns out we actually get a tensor category which was recently proved to be equivalent to the category for a quantum SL2 category, actually, at a root of unity. This is a recent result by Terry Gannon and Chris Negron. So, and probably we would expect many other examples like this with higher ranked W-algebras as well. Okay, so that's all of my talk.